Hey everyone, welcome back to the Explainer. Today, we are jumping headfirst into the high-stakes world of system engineering. We usually think writing the code is the finish line, right? But as we're going to see today, building the software is literally only half the battle. The other half? Trying to absolutely destroy it.
So everything we're talking about today basically revolves around one ultimate standard of success: building a robust system. And by robust, we mean a setup that actually survives the sheer chaos of the real world without crashing and without losing your precious data. Because let's be honest, on the flip side is that universal nightmare we all dread: fragile software that just gives up right when you need it most.
Okay, let's dive into this contrast because it's pretty stark. On one hand, you've got the ultimate fear, right? Fragile software going live way before it's ready, leading to crashing servers and massive data loss. Nobody wants that. But once a system is mapped out on paper, it has to be built and then rigorously tested to reach that goal on the right: a rock-solid, robust architecture that can handle literally whatever the real world throws at it.
All right, here is our mission plan for today. We're going to cover building and breaking, the modular approach, interrogating the system, the weapons of a tester, creating the test plan, and finally, the engineering lifecycle. Let's get into it.
Section 1. Building and breaking. So what exactly are we building?
Well, before we can test anything, we really need to wrap our heads around what the developers are actually creating. We're essentially looking at three core components here. First up, file structures. This is the underlying database architecture that keeps our data secure. Then, user interfaces, the front-end layouts, the buttons, the logic that manages how humans actually interact with it. And third, hardware integration, because, code doesn't just exist in some magical vacuum. It has to interface flawlessly with physical stuff out in the real world, like scanners, printers, and touchscreens.
Section 2. The modular approach. Building things in pieces.
All right, so now that we know what we're actually building, how do we stop the whole thing from catastrophically collapsing during development? It's simple, really. Do not build a monolith. If you try to build a giant monolithic system all at once, you're basically creating a massive black box that just buries errors deep down inside the codebase. And when it inevitably fails, you'll have absolutely no idea where to start digging. So instead, engineers use a modular system. By building in isolated, manageable parts, you can catch bugs super early. It's essentially quarantining failures before they can take down the whole ship.
Think of it like a giant puzzle. Individual modules are meticulously inspected all on their own before their edges ever even touch. They only slide together to form the complete working program after every single foundational piece is already proven it can stand on its own. The whole pipeline here is highly systematic. First, programmers write the individual pieces. Then, testers interrogate and fix each of those modules independently. Only then are they combined into the final program for a full system test. And that final step? It's not just a repeat. It's a targeted hunt for data clashes and memory leaks, things that only trigger when these isolated parts are forced to talk to each other for the very first time.
Section 3. Interrogating the system. Time to hunt for some flaws.
So we're pivoting now. We're moving away from the builders who lovingly craft the software over to the breakers. These are the engineers whose entire professional purpose is just to hunt for weakness. But think about this for a second. Once a sprawling digital system is actually built, what exactly do we test? Like, where do you even begin looking for flaws in a million lines of code?
Well, you start by mapping out the interrogation points. Testers systematically trace the flow of information. They check data structures, asking, are dates actually stored as dates? They verify file structures to make sure data retrieval is reliable. They monitor input and output formats so the end results are exactly right. And absolutely crucial here, they stress test validation rules. They have to make sure the system actively, almost violently rejects any silly, malformed, or literally impossible data that some human might type in.
Section 4. Weapons of a tester. Stress testing the boundaries.
To pull off this kind of interrogation, these breakers need a very specific set of tools and, honestly, a pretty ruthless mindset. Let's call it the Breaker's Manifesto. You cannot test a system by only being nice to it. Right? If you actually want to prove a system works in the messy, chaotic real world, you literally have to try and break it. To do that, testers wield an arsenal of 4 specific types of data. First up, normal data. These are your completely acceptable middle-of-the-road inputs that the system should just breeze right through. Second is extreme data. This pushes the absolute outer edges of the allowed boundaries. Third, abnormal data. This is entirely wrong data types or out-of-bounds information, which the system absolutely must aggressively reject. And finally, live data. This is real historical data, usually imported from an older legacy system, just to prove the new architecture gets the exact same known outcomes.
And this brilliantly illustrates the concept. Have you ever accidentally typed a letter into a phone number box on a website? Well, testers do that on purpose. Imagine a temperature system calibrated only to accept inputs from 21 to 50 degrees Celsius. 35 degrees? That's our safe, normal data. But testers will hammer the extreme boundaries precisely at 21 and exactly at 50. Then, they push into the red zone with abnormal data, typing in -10 or literally typing the word 50 with letters, just to prove the validation rules hold up under absolute pressure and trigger a controlled error instead of a complete system crash.
Section 5. Creating the test plan. How we document quality.
Now, this whole breaking process might sound like pure chaos, but I promise you it's meticulously documented. Engineers use a professional standard called a test plan. Think of it like an airtight recipe that guarantees not a single interrogation point gets missed. Every test requires 4 core elements: the test ID for tracking, the specific data input that's being weaponized, the expected outcome, and finally, the actual outcome of what the system actually did when it was under attack. This dashboard is where all that chaos gets tracked and tamed. By lining up the expected outcome right next to the actual outcome, we can mathematically prove the system's quality. Let's jump back to our temperature example. You track the exact inputs, the 35, the 21, the 51, and the -5. And notice that for the abnormal data, the 51 and the -5, the expected outcome is a rejected error. When the actual outcome matches that expectation, boom, it proves the system successfully defended itself.
Section 6. The engineering life cycle. Taking it from blueprint to reality.
So we've seen the building phase and we've explored the breaking phase. But in reality, these two things connect in a continuous, ongoing loop. We start at development, actually writing the modules, then we flow right into testing, interrogating those modules to catch any data clashes, and finally validation. This is the ultimate stress test using our normal, extreme, abnormal, and live data. And if it fails, well, we loop right back to development. The absolute crucial takeaway here is this: a software system is only as robust as the test designed to break it.
Which brings us to one final thought for you to chew on. Think about the banking app on your phone, the software running your car, or even the medical databases at your local hospital. Are the digital systems you rely on every single day truly robust? Or are they just sitting there, completely untested, waiting for the exact right piece of abnormal data to completely break them? Definitely something to keep in mind the next time a screen freezes on you. Thanks for joining me on this Explainer, Focused Learners. Keep asking those big questions, and I'll see you next time.